Hello. The purpose of this video is to demonstrate how ANSYS CFX can be used to solve one-dimensional transient diffusion in a solid. This will build directly upon the steady-state 1D diffusion tutorial, so you definitely want to watch that and work through that first before attempting this one. So I have opened Workbench and I've opened my previous 1D diffusion problem and I've saved it now as another file. I can open up the results and through that view the report that I created. We can see that for my domain I used 100 mesh elements across my 1D plane wall, and I can also see the temperature distribution that I created through that plane wall. Again, it's parabolic because I have heat generation inside the wall and I have a fixed temperature condition on one boundary and I have a convection heat transfer on the other boundary. Okay, so I will close that, and what I would like to do is modify this by turning off the volumetric heat generation and then solving this as a transient problem to observe how in time the temperature changes until a new steady state value is released. To modify my file, I will start by entering CFX pre through the setup cell. Now that CFX pre is opened, I can start to change my settings to make this a transient solution. Again, working my way top down, the mesh has already been imported. I'll now click on Analysis Type. You can see that has the clock symbol next to it. And this is where I identify that instead of a steady state solution, this is a transient solution. And now that opens new options for me. The first is how long of a time duration do I wish to model. This is a trial and error type setting in this case, so I'll choose 5 minutes. Next, the time steps that you wish to use. And again, this is a trial and error. You can set a time step, then observe the solution, compare that with some benchmark data, then you can go back, reduce that time step, see if it changes your solution any to have confidence that your time step is not a dependent factor on your solution. So for instance, I might choose half a second for my time step, and then I'll start at 0 seconds. Okay. For initialization, I will actually delete that since I'm going to start from my steady state solution. That will be my starting point. And then at time t equals 0, what I'm doing is going into my subdomain and I am turning off any heat generation that was occurring. Okay, moving further down into solver control. I think I can keep these settings as they were. If I look down in my message box now, I see a few things of interest. One is it's saying that transient analysis require initial conditions specified unless you point to a file at the runtime. And that's exactly what we're going to do. So we can disregard that message. And then it offers a second warning stating that no intermediate transient result files have been defined. If I don't set that, then all I will have is the final value after 5 minutes has passed. I'd rather save the solutions at intervals throughout, so I will go into Output Control, Transient Results, and I will create a new Transient Results control. And I will set the time interval. So I'm running for 5 minutes of simulation, and let's say I'd like to save a solution every 5 seconds, for instance. Okay. Note that I still have a monitor point where I am monitoring the maximum temperature in the domain, since temperature is of interest to me. Note that if you were interested in monitoring the temperature at a certain point, you could do that through the Cartesian or cylindrical coordinates and just choose monitoring temperature and then inputting your coordinates. I'm fine with what I had though, so I will just click close, which keeps my previous input of the maximum temperature in the domain. Okay, so I've turned on the transient analysis. I've changed and turned off my uniform volumetric heat generation, and I have also changed this to save a solution every 5 seconds. Now I can close and I can start the solver program. Okay, double-clicking on the solution cell will open the CFX solver. And it is at this point I need to specify my initialization. The default is current solution data if possible. If my previous solution was the steady state solution, then it will automatically identify that results file and use it as the starting point for the simulation. Another option is to choose initial conditions and then activate the specification box. Then you can click on the file name to choose the results file directly. And so we will try that for this. And you will want to go to the CFX directory under which you saved your previous solution. Okay, I've jumped ahead into my folder, and you can see that I named this project 1D Diffusion Transient, and therefore there's a 1D Diffusion Transient Files directory. I can open that, and DP0 stands for Design Point 0, which is the default. I click on CFX and CFX, and you see that I have a couple of results files from previous runs. Now they don't have to be in this directory. If my steady state solution was saved in another file, I could access that file and get the correct results. The results, by the way, are identified when you do a solution in the workspace. It will identify what run that is. For me, I'm wanting to grab the fluid flow 002 results file. And instead of continuing the history from that point, I'm going to start over for this, since I want to start at time t equals 0. So I will click Start Run, which should now take the previous results file, load that as the starting point. Okay, again, it is loading the new file conditions that I set in CFX Pre. And you see the solution process begin. It's going by pretty quickly, but it's moving forward every time step, or 0.5 seconds as I have specified in time. And per the default controls, it's running a maximum of 10 iterations before continuing. Now this doesn't really tell me much. What's much better is looking at your monitor point. And remember that I chose to monitor the maximum temperature in my domain. So we can see accumulated time step. Something better would be to right-click, choose Monitor Properties, and under Range Settings, change the workspace default to the simulation time. Okay, so this is the elapsed time of the solution. And what we see is my steady state solution had a maximum temperature, the peak of the parabolic temperature profile, of about, 387 degrees Kelvin. And as I turn off volumetric heat generation, I would expect my 1D plane wall solution to be a simple linear profile. The transient variation of that, however, is some sort of exponential decay, and I see that. And then after about 120, 130 seconds, I see that I've already reached steady state conditions. Temperature is no longer changing with time. So I can go ahead and stop the simulation early through the stop button. And it tells me it completed normally. I can look and see I still have well below 1% imbalance in conservation of energy along my boundaries. I can also see that these were all the solution files written at each of the 5-second time steps that I specified through the solution. And it tells you the directory in which they're saved as well. Okay, so I can now close the Solver Manager. Wait for, okay, this is the check symbol with the pause indicating that I stopped the solution prematurely. But now I am in a position to open the results cell and analyze the data using CFD post. Okay, I've now opened the post processor, CFD post, and you can see that at default it loads the last time solution, which was 250 seconds for my specific instance here. And I can click on my report viewer, and I can see my 100 control volume mesh. I can see a contour plot of the temperature profile through the wall. Doesn't really show me much. Note that I only see the lower temperature scale because this is scaling according to the temperatures over the entire time solution. We started out at much higher temperatures. Probably better or best to view in this case would be a chart plot of temperature along the distance of the wall. And you can see that I have a fairly linear temperature profile, which is what I would expect for 1D conduction at steady state with constant properties. I have my fixed temperature boundary condition at one end. At the other boundary, I have my convection boundary condition. If I want to observe intermediate time steps, I can do that by, let's see, for instance here, I'll just click on the chart directly. So I have that activated. And I can click on the time icon, which opens a time step selector. So instead of the final 250 second solution, for instance, let me load the initial, and I can see that now has been loaded. I could move forward to 30 seconds in time, 60 seconds in time. I believe you can create a video animation. I'm not an expert at that. You could look at the help material to get more information. Probably one of the most useful things in this instance would be on one plot to create several curves at different time steps to show the evolution of the temperature profile. I think one of the easier ways to do that would be through the export button on the chart. So you could, for instance, load your initial solution, export that data to a comma-separated variable file that you could load into Excel, and then you could do that at several other time steps along the way, and save that data and import them into, for instance, one Microsoft Excel plot showing the evolution of the temperature profile. Remember as well that if you're wishing to determine how long it takes for steady state to be achieved, the best place to do that is actually in the solver through a monitor. So if I don't want to solve again, if I just want to go and observe or edit the solution file from previously, I can right-click and choose Display Monitors, and that will open the previous run, which is run 003. And for my user points, again, I chose to monitor the maximum temperature. You could monitor the temperature in one location in space, for instance. But what I have now is a plot of how that varies with time, and this is a good way of indicating when steady state is achieved. Again, this could also be exported by right-clicking and choosing Export Plot Data. And finally, just because this appeared to work correctly does not mean that it accurately solves the problem at hand. On one hand, we have verification. Are we solving the numerical approximation to the diffusion equations correctly? And then also validation. In this case, does the diffusion equation really represent an accurate model of the real-life phenomenon I'm trying to model? In the first case, the only way we can determine whether our model is verified is by reducing the space step and the time step, and seeing if either of those changes our solution appreciably. If it does, then we know we have not converged on a solution and need to further refine our grid in space and or time. In terms of validation, you can compare, for instance, against a known solution. We're doing one-dimensional conduction in a plane wall, so we have analytical solutions on hand to compare against as a validation. But with this, we're able then to run through a transient solution of one-dimensional diffusion, in this case conduction heat transfer.